In this video, we are going to discuss the properties of cross products. And as you can see, there are several. Let's make note of this first one here. We've discussed already that the cross product between two vectors is not commutative. That means that A cross B is not the same thing as B cross A. But if we were to negate the B, we have A cross B is actually equal to the negative of vector B cross A. So it is not commutative. The cross product is not commutative like the dot product is, but we do have a property that feels kind of similar to that. Notice also that we've got some properties down here. C in this case is a scalar quantity, meaning that this is going to be a scalar multiple of my A vector, right? It's just going to elongate it or perhaps flip that vector into an opposite direction. So C is a scalar multiple of the A vector, and then that scalar multiple can be pulled out to be multiplied by the resultant of cross-producting A and B, or we could move that C scalar onto the B vector, and all of these cross products would give us the same vector output, the same vector resultant. The cross product property that we're going to prove in this video is the third one. It is that the cross product does enjoy something that looks and feels similar to the distributive property, right? If I have vector A crossed with B plus C, we can think about that as being distributed in to where the resultant is going to be the A cross B vector added to the A cross C vector. So the first thing that we're going to want to do to prove this property is to generalize our A, B, and C vectors. And then we're going to take a look at what the B plus C vector would look like. And we're using pointy bracket notation here because this is going to get quite involved, and I want to keep our notation as streamlined as possible. So this vector is going to be B1 plus C1, B2 plus C2, B3 plus C3. These are the components of the B plus C vector. So now we're going to take our A vector and cross product it with the B plus C vector. Essentially what we're doing is going to use the proof by deduction method, which is where we begin with the left-hand side of what it is that we're trying to prove, which is that A cross B plus C is equal to the right-hand side, but instead of jumping all that far, we're going to take smaller steps until we generate the right-hand side of the property. So A cross B plus C, we're going to use our theoretical determinant in order to determine that. So we've got IJK here, and our first row of our matrix is going to be the A vector components, and the second row of the matrix is going to be our B plus C vector components. So we've got B1 plus C1. Notice we are being extremely careful to ensure that we have vector hats over anything that is a vector, and the scalars do not have vector hats. So now we're going to isolate this top left corner element and eliminate the row and column that contain that I vector, and so we'll say this is then going to be equal to the I multiplied by the 2 by 2 determinant of the matrix that remains if I eliminate that row and that column. So we have A2, A3, B2 plus C2, B3 plus C3, closed determinant, and then minus J multiplied by the 2 by 2 determinant that results when I eliminate the I and J row and column, and we have A1, A3, B1 plus C1, B3 plus C3, and then we are going to add the K vector times its 2 by 2 determinant. So we'll eliminate the row and column containing the K, and the resulting 2 by 2 matrix that remains is A1, A2, B1 plus C1, B2 plus C2. And now we will go ahead and calculate those determinants. So the I vector is going to be multiplied by A2 times B3 plus C3. So we say A2 times B3 plus C3. And then from that, we're going to subtract the product of the other diagonal, which is going to be A3 times B2 plus C2. Now, this is a lot of parens, so I'm actually going to make these outermost parentheses brackets just to kind of keep it all separated. And then we have minus J times big old bracket of the determinant of that 2 by 2 matrix that remains there. And then our K vector is then going to be multiplied by its determinant, or the determinant of the matrix that is in the 2 by 2 matrix there beside it. So we've got A1 times B2 plus C2 minus A2 times B1 plus C1, close and close. So this is a lot of stuff going on here, and remember, this is basically what that left-hand side is turning out to be when we actually calculate that determinant. So we're going to essentially keep on cleaning it up. I'm going to clean this up and at the same time switch it over to pointy bracket notation and get rid of the IJKs. So I'm just going to be looking at the corresponding or the resulting components. Now, in this step, I'm also going to distribute the A2n, the A3n, and then see what that first component or the I component leads us to. So we're going to have A2B3 plus A2C3 minus A3B2 minus A3C2, essentially just distributing in those A values. Now in this next one, we're going to distribute in the A values again, but we're also going to distribute in this negative. So what that's going to yield in this very first little bit is negative A1B3 minus A1C3. Now when I distribute the negative into these terms, I'm going to get plus A3B1 plus A3C1, and that's my second component of this resultant vector. And the last component of this vector is going to be determined by distributing the A1 and the A2 into these parens, so that last component is then going to be A1B2 plus A1C2 minus A2B1 minus A2C1, which is a very big and complicated vector. Again, this vector is the result of taking A and crossing it with B plus C, and we want to show that that's equal to the other side of the property, which is A cross B plus A cross C, and it may actually benefit us to look at what A cross B actually looks like, what A cross C actually looks like, so that we can see a little bit easier what it is that we are trying to make our vector approach. So by definition, A cross B is A2B3 minus B2A3, or let's call that A3B2. And the rest of that follows here, A3B1 minus A1B3, A1B2 minus A2B1. And similarly, for A cross C, we're going to have A2C3 minus A3C2. And then here's the rest of that vector. So what we're trying to get towards is an I component that looks like essentially these two things that are added together, right? Because we want the cross product of this vector times the cross product of these vectors added. So it's going to be essentially adding those components together. So we want to see if where we are with our current process is the same as these things added together. So can we rearrange the terms of these components to match what it is that we're headed towards? So let's see, A2B3 and then minus A3B2, and then to that let's add the other two components, which is A2C3 minus A3C2, and it does look like we're going to be able to get there. So let's rearrange these other terms, we have A3B1 minus A1B3, and then we have A3C1 plus minus A1C3, and then for our third component we have A1B2, so let's cross that off, minus A2B1, and then A1C2 plus minus A2C1. So let's split this up into the sum of two vectors. So that looks like it's going to be the vector A2B3 minus A3B2 as the component, the I component of the first vector. The j component of the first vector is going to be A3B1 minus A1B3. The k component of the first vector is going to be A1B2 minus A2B1, and that's the first vector that we have, to which we're going to add another vector, which is A2C3 minus A3C2, A3C1 minus A1C3, and then our k component is A1C2 minus A2C1, and that's the second vector. So what we see here is that the first vector here that we have is the cross product of A and B. And then to that we are adding the second vector that we see here, which is the cross product of A and C. So conclusion time, we say therefore A cross the sum of B and C is going to be the same thing as A cross B plus A cross C, which was to be proved. So we do our little I'm done box.